Hello everyone. So today I will teach you with the help of my notes. So our next topic is the classification of the turbine, classification of the steam turbine based upon the shaft orientation. Based upon the shaft orientation. Okay. Let's just take this color. Okay. So first is this tandem compounded. What is tandem compounded? In the tandem compounded, two turbines are joined with each other like this. Okay. So the first one is the high pressure turbine and second one is the low pressure turbine. High pressure and low pressure turbine. The here but we can say that here first one is the high pressure turbines and the second one is the intermediate pressure turbine and the third one is the low pressure turbine. So when the turbines are attached with one by one, then this is called the tandem compounded turbine. And the second time is the cross compounded turbine. Cross compounded turbine is it is seen here. Like here the turbines are attached uh, by cross in the cross section direction. If I'll explain you, let's take this. Okay. Like here we are seeing that the steam is coming from here, it is going from here, then it is coming out from here, then it is going after coming from the intermediate pressure turbine, it is going through the two low pressure turbines. Okay. Now when the steam comes in between the low pressure turbine, then steam comes from this direction and this direction, this direction and this direction, and thus the turbine rotates and we can get the power output from the generator. Okay. So in uh, tandem compounded assembly, all the turbines are connected to a single rotor attached to a single generator. Okay, like we have seen in the figure. And in the cross compounded turbine, uh, the assembly in the assembly, two separate shafts are used to run to separate generator, normally at different speeds. So the first series and second series are in different speeds. Okay. Used to run the separate generator, normally at different speeds. It is normally preferred where the volume to be handled at lower stage is very high. Okay. So here you can see that it is used where the at lower stage, when volume becomes very high, then we are using the cross compounded turbine, and when it is not, then we use the tandem compounded turbine. Fine. So the next topic is the turbine specification. Turbines are specified by shaft orientation followed by steam flow path for low pressure turbine, and finally last stage low pressure turbine blade height in inches, like TC2F14. It means that tandem compounded turbine is prepared by the shaft orientation followed by steam flow path for low pressure turbine, and finally the last stage low pressure turbine blade height. So this 14 is in inch. It is actually the height of the it is actually the height of the low pressure turbine. And what is 2F? It is the shaft orientation followed by the steam flow path. This is the shaft orientation and the steam flow path for the low pressure turbine. Like CC cross compounded 4F14. This is the shaft orientation by stream flow path. 4F is the shaft orientation. Shaft orientation by stream flow path, and this is the blade height in inches. Now let's will describe the simple impulse turbine. So simple impulse turbine is also called the D-level turbine. Somewhere it is called D-level turbine. So as we have seen earlier, that simple impulse turbine, there is a set of nozzle and moving blade. So in the nozzle, because nozzle is stationary, so in the nozzle we know that pressure drops, and in the moving blade, because there is not any specific orientation of the blades, so the pressure remains constant and the velocity increases then decreases, as we have studied earlier. And the velocity can be given as the drop in enthalpy, and the blade velocity is half of the steam velocity for maximum efficiency. So absolute steam velocity is around 1100 to 1200 meter per second. So the blade velocity will be 550 to 600 meter per second. Okay. So we can calculate the blade velocity from pi dm by 60, because the RPM is around 12,000 to 15,000 RPM. So the simple D-level turbine is the first working impulse turbine, consists of a single set of nozzle and moving blade. The total enthalpy drops takes place in a single nozzle, which results in a very high rotational speeds, exceeding much above the frictional limit. Practical limit, exceeding much above the practical limit required for electricity generation. So the main problem of the D-level turbine is its speed is very high, like 20,000 to 12,000 to 20,000 RPM. Its speed is very high, so we don't need such a high speed. Okay, so we need to control this speed. That's why we use the technique compounding. So we'll study here the compounding of impulse turbine. So what is compounding? So compounding is a method of reducing the high rotational speed of simple impulse turbine. It is just a method of reducing the high rotational speed of simple impulse turbine to bring into practical limit required for electricity generation. Okay. So the first compounding is the pressure compounding, which is called ratio turbine or chow turbine. Okay. So here in this we do that we use a set of nozzle and moving blades. Okay, like nozzle and moving blade. So as we know that in the nozzle pressure drops gradually, then in moving blade pressure constant, then again in the nozzle pressure drops, then again pressure constant, pressure drop, pressure constant. So pressure is continuously decreasing. And what about the velocity? We know that velocity in the nozzle increases, then moving blade decreases, then increases, decreases. Okay. But at the end, some pressure is lost because of the frictional effect. 2 to 2% velocity is lost. So here what we can see that what is the velocity of D-level turbine? D-level turbine is the difference of the pressure drop of a single stage. It is the single stage for single stage. Okay, this is for single stage for D level. So for the ratio, for the D level turbine is the single stage. This is the velocity for the single stage. Okay. So delta H is for single stage, like this is the single stage. Okay. So what will be the velocity of the ratio turbine? The velocity of the okay, here we can see that for the 4 stages, the the enthalpy drop delta Hs is equal to delta H by 4. Here actually delta Hs, what is delta Hs and delta H? Delta H is actually the all over pressure drop, and delta Hs is the pressure drop in a single stage. Okay, so here we can understand that here it is written that delta Hs is equal to delta H by 4. So it is clear that delta H is the enthalpy drop through the whole stages, and enthalpy drop through the single stage will be the 1/4 of that is the whole stages. So if we want to calculate the velocity of the rotary turbine, then that will be proportional to the single stage. Okay, so the single stage enthalpy drop will be delta H by 4. Okay, that will be delta H by 4, that is Vd by 2. So we can say that the velocity of the rotary turbine is equal to d level turbine by 2. If there are 4 stages, for n stages, velocity of the rotary turbine will be Vd by root n. So here we can see that because velocity is equal to pi dn by 60, so because velocity of rotary is decreased, so the RPM will be decreased. Fine. So in this type of turbine, compounding is done for the pressure of steam. For the pressure of steam, that is total pressure drop is arranged in more than one stage. Each stage consists of a set of nozzle and moving blade. Now as the enthalpy drop in each stage is decreased, it decreases the rotational speed. Like the enthalpy drop, if I draw like this, the enthalpy drop is delta H here. So the enthalpy drop in a single stage, delta Hs will be delta H by 1, 2, 3. If it is 3, then it is 3. For 4 stages, it is 4. Fine. This is the pressure compounding, in which we reduce the pressure, and by reducing the pressure, because the enthalpy drop reduces, so the velocity reduces. We can also do the compounding with the help of velocity compounding, in which we continuously reduce the velocity. Then how we can reduce the velocity continuously, which is done by the Curtis turbine. In Curtis turbine, we use the velocity compounding. So in the velocity compounding, in the first stage we use the nozzle and moving blade setup. But in the next stages, the stages will be the fixed blade and moving blade. So what happens that in the nozzle, first pressure drops, in the moving blade pressure remains constant, and in the fixed blade also pressure remains constant, because there is not any variation of the area. There is not any variation of the sectional area or sectional volume. That's why pressure remains constant. Okay, but what about the velocity? In the velocity, we can see that from the nozzle, first velocity increases, and we know that in the moving blade, because it is moving, the velocity decreases. But in the fixed blade, why the velocity will change? No change, because the cross-sectional area is same, so velocity remains constant. But again in the moving, velocity drops, and then fixed blade velocity constant, and then velocity drop. So this is the velocity compounding, in which we use the set of moving blade and fixed blades. So moving blade is just doing nothing. There is no need of, we can also do that, there is no need of using moving blade, because if you want to decrease, then it can continuously decrease. But the point is that when the steam will come here, then we need to give a direction so that it can flow from here. Okay, If I just remove each and everything. Okay, so what I'm saying that here it is just giving for the path to the steam, so that it can easily and smoothly flow through the blades of the turbine. That's why we are using the fixed belt. It is not necessary, but it is required. But in the case of pressure compounding, it is necessary to use the nozzle so that we can decrease the pressure. Otherwise there would not be any change of pressure, because in the moving blade pressure is constant, so it is the necessary to use the nozzle here. But in the velocity compounding, uh, use of fixed belt is not required, but it's necessary to use so that we can give the direction to the velocity of the steam. Okay, so we can say that in this type of turbine, compounding is done for the velocity of steam, that is total velocity drop is arranged in more than one stage, and each stage consists of a set of fixed and moving blades. There is a single nozzle in which total pressure drop takes place. There is a single nozzle in which total pressure drop takes place. Okay, the high velocity obtained is converted into work in more than one stage. High velocity, which we are getting the high velocity, that is converted into work in more than one stage. Okay, so here we can say that the velocity decreases, but the power is increasing. Okay, we will use that power, we will use that momentum or power for the long time. Okay, so we can say that simple turbine for single stage is called D level turbine, pressure compounding is called ratio, velocities compounding is called Curtis turbine, 50% extent turbine is called Parsons turbine, and 100% extent turbine is called Hero's turbine. We'll study further. Okay, now we will see the velocity diagram for impulse turbine. Okay, so I think I should draw it. Okay, velocity compounding, latest draw. Velocity diagram of sorry I have to draw velocity diagram of impulse turbine. So for that, first of all I will draw the 3D diagram. Let us say that our steam is flowing from this direction, and our turbine is oriented like this. So blade will be arranged somewhat like this in this direction. Okay, so the blade will be like this. Okay, are you getting? Blade is arranged like this. Okay, so what I'm trying to say that our blade is this one, this one, or if this one is our blade. Okay, and this one is also, and this one is also our blade. This is also okay. Somewhat it is able to visualize. Now I will take this section of the blade, and I will draw like this. it is somewhat curved. So let's say that uh, our steam is coming from this direction, which is v1. Okay, and because it is curved in this direction, so the relative velocity will be the tangential to this, and this is our base, so the relative velocity will be in this direction. This is the basis of the velocity diagram. Okay, first of all draw the absolute velocity diagram, and then the relative velocity diagram. And now use the mathematics. So what is mathematics? Vr1 is equal to v1 minus u1 minus u1. So you can say that v1 is equal to vr1 plus u1. It means that if you want to find out v1, then you have to add u1 to vr1. So the u1 velocity will be in this direction. This is our u1. Fine. And we can also get the other velocity. Let's say the different color. This is called the this is the component of the absolute velocity, and we call it vf1, flow velocity. And if we'll define the angles, so this is the absolute velocity is denoted by alpha, and the relative velocity, because it is showing the blade angle, it is denoted by theta. Okay, and the tangential component, that tangential component around the along the blade, that is defined as, that is very important velocity, vw1. Okay, now I will draw directly the outward velocity diagram. Okay, so first of all you can draw that relative velocity will come like this, vr2. Okay, and when we will add u2, and because it is impulse turbine, okay, so in the impulse turbine u1 is equal to u2, keep in mind. Okay, u1 is equal to u2. So to find out the v2, you have to add u2 in vr1. Means just a minute, I have to get some more space. Okay, so first of all, let's say it is our vr1, vr2, and when we add u2 in this, but u2 is u1. Okay, then we'll get v2. Okay, and this is the horizontal component, vf2. Okay, now this is the blade velocity phi, and this is the beta outward velocity, or outward angle of the steam velocity. Okay, and its component, this component will be vw2, which is outward world velocity component. Okay, now this diagram can be drawn in a single diagram, because we know that the blade velocity is u1. Okay, and we are getting the v1 velocity, we are getting v1 is equal to vr1 plus u1. So when you will add vr1, then you will get no, I should not draw from this. I can draw this you will get V1. And when you will add, when you want to get V2, then you will add VR2 plus V1. Okay, so its direction is this, VR2, and you get V2. And you can also denote the angles, like VR1 is the blade angle, blade inlet angle, that is denoted by theta. VR2 is the phi, blade outlet angle. V1 is the let's denote from other color. This is the V1, so it is alpha, and this is beta. Fine. Now in this figure there will be some slight information involved, like that upcoming velocity components, there is a slight change like this one. Okay, like in this figure we can see, if I'll show you in this figure, you can see that, as I have already mentioned, the angles and the different velocity components. So here I want to catch your attention here, that this flow component is this and this flow component is this. So we are seeing that Vf2 is less than Vf1. Okay, Vf2 is less than Vf1. It means that this is more. This is called the axial force component. How you can get the axial force axial force component? By the rate of momentum change. Axial force component you can get mass of steam into Vf1 minus Vf2. Axial force which is applied on the impulse axis. Now this diagram is showing the impulse effect. This is the impulse effect. This we want from the impulse turbine. This is our impulse effect. There is not any reaction effect involved here. And this is the tangential effect, Ft. Tangential effect, we are getting to rotate the blades. Tangential effect, whatever the tangential component we are getting in this direction, Ft. This is rotating the blade, and axial component we are getting in this direction. This is pushing the turbine in forward or backward direction according to the steam direction. Okay, axial force. And this is the impulse force at an angle which is occurring on the blades. Okay, so from this figure we have to understand something, that theta is equal to phi, because blade angles are symmetrical, blades are symmetrical, so theta is equal to phi, and blades are, because frictionless, then VR1 is equal to VR2. That's why we are getting this type of diagram. Okay, like you are saying that if VR1 is equal to VR2, then why are we are getting the extra force here? Okay, because of this distance. You can see the distance here. Okay, if you will see the triangles, formation of triangle, then you will get to know that VR1 is equal to VR2, because we are assuming here that blades are frictionless. If friction is null, then VR2 is equal to K VR1. Usually practically K is equal to 0.9, which is called blade velocity coefficient. So ultimately we want to find out the work per stage. So work per stage, we can get the mass flow rate of the steam, and VW1 plus VW2 into U. This is the force, and into u, when we multiply with the velocity, we are getting the power. So it is the power, you can say power of the impulse turbine. So though how we are getting this formula, we can see from this, that vw1 we are getting in this direction, and vw2 we are getting, sorry, vw1 we are getting, vw2 we are getting in this direction, and vw1 we are getting in vw1 we are getting in this direction. Okay, so to you want to find out the tangential force. The tangential force will be P1 minus P2, rate of change of momentum initial minus final. So what is the rate of change of momentum initial? M dot Vw1 minus M dot minus Vw2, because in opposite direction, so it will be M dot Vw1 plus Vw2, which we are getting here. That's why there will be a plus sign in turbine, in case of turbine. Okay, if n stages are there, then you have to multiply with the n. W per stage is denoted by W stage. This is called trim or blade diagram. Tangential force Ft is equal to m dot Vw1 Vw2, as I have derived power in this. Okay, so in the work, this is the power only. Okay, and axial force will be Vf1 plus Vf2. So here it is minus actually. Energy lost in the moving blade due to friction will be m dot Vr1 square. It is just kinetic energy initial minus kinetic energy final. So m dot half m dot Vr1 square minus half m dot Vr2 square. If the relative velocity is same, means friction is same, then there will be no kinetic energy loss. But there is friction everywhere, so that is called energy lost in the moving blade due to friction. Fine.